This video is a continuation of Gauss's law. In mechanics, we talked about a mass distribution, where mass was evenly distributed over a long cylindrical rod. Here, we're going to talk about uniform charge distribution, where charges are spread evenly on or through an object. Now, we know that for conductors, excess charge is always found on the surface of a conductor. Therefore, uniform charge on a conductor will be spread evenly over the surface of the object. For insulators, charges remain where they are placed. So, when it comes to an insulator, you need to be told where the excess charges have been placed. Often, problems will state that the excess charge is distributed uniformly throughout the volume of the object. So these are a couple of key words we're going to be looking at when we look at problems. So charge density is the ratio of charge to either length, area, or volume. So, when charges are distributed uniformly, the ratio of charge to either length, area, or volume will be the same no matter which portion of the object you sample. And this is going to be helpful when we start looking at different shapes to be able to understand what this means. So in this example, we show that 1 coulomb of charge is placed on a rod that is 10 centimeters long, and it is divided into 10 1 centimeter increments. Again, each increment has 1 coulomb of charge. So the amount of charge per unit length is the same no matter how many plus or positive signs we look at. So lambda is equal to Q over L, the charge distributed over the entire length. So if we only look at the first one, we're doing 1 over 0.01. If we look at 3 of them, it's 3 over 0.03. But no matter what, the charge density does not change. We still have 100 coulombs per meter. So again, we're going to look at a couple of different charge densities. This is a linear charge density. This is very similar to a linear mass density, where we had a mass distributed over an entire length. Well, here we have a charge distributed over an entire length. Usually this is used for very thin, long rods. So lambda is going to represent the linear charge density, which has units of coulombs per meter. Q is charge, and L is length. This is a surface charge density, which means that the amount of charge is uniformly distributed per square meter of surface area. So this is represented by a sigma, which is charge over area. So R sigma is surface charge density, Q is charge, and area is meters squared. So often for spheres, we're going to be using Q over 4 pi R squared. And cylinders without the ends is going to be Q over 2 pi RL, which is the surface area of a sphere. This is volume charge density. This is the amount of charge per unit of volume. This is going to be represented by a rho. It's often used for spheres and cylinders. In this first example, we have a solid sphere made of conducting material that has a radius of 2 meters and is charged to 4.4444 times 10 to the negative 9 coulombs. Part A says, using Gauss's law, derive an expression to determine the electric field in the vicinity of the sphere. So, started with Gauss's law. And we know that the right-hand side is the charge enclosed over epsilon naught. Again, if our Gaussian sphere makes our electric field constant at the edge of it, then it's going to come out of the integral. Now, I am showing this derivation again. It is important that you're able to do it. It will come out on your test, and it will come out on the AP exam as well. So, our change in area here, again, is a sphere. And we want to use this to solve for the electric field. Again, this doesn't normally show up on our final answer, so we can simplify this to include our k, which is 1 over 4 pi epsilon naught. Again, this is just a constant. So we've used this equation to solve for the electric field in the vicinity of this conducting material. So for part B, we're trying to determine the electric field at point A. So we're going to use the equation that we just derived. And we're going to draw or create a Gaussian surface at point A. Now, since point A is right in the center and we cannot draw a circle around a point, then our charged enclosed would actually be 0. Another way to think about this is because this is a conducting material, this is a conductor, that means all of our charge is placed on the outer surface of this conductor. So there actually is no electric field inside. So our electric field at point A would be equal to 0. So we could graph that here. In part B, we're asked to determine the electric field at point B. Now, we want to draw a Gaussian surface through point B. So again, these are just imaginary surfaces. And we want to use the equation again that we derived. Again, because this is a conducting material, we still have no charge enclosed at point B. So, our electric field is still 0. So part D asks us to determine the electric field at point C. Now, we can draw a Gaussian surface at point C. Again, we needed to match the surface that we're looking at. Here we can see that our Gaussian surface is going to enclose the entire charge on our actual sphere. So, to find the electric field, we can simply plug in all of our values. So for K, we have 9 times 10 to the 9th. Our charge enclosed is 4.4444. And our distance r is actually just going to be the radius of this sphere. So 2 squared. And you should get an electric field value of Newton per Coulomb. So we can plot that here. In this problem, we're trying to solve the electric field at point D. Now, it didn't tell us that each letter is a meter apart, but our radius is 2 meters, so we can assume that that's happening. So, to solve for the electric field, again, we can use our equation. Now, the charge enclosed is the same charge that was enclosed in part C. But now, our distance has changed. So our distance has now increased to 3. So this is 4.4 Newton per Coulomb. And we can plot that in our graph. For part F, we're asked to determine the electric field at point E. Again, the same charge is enclosed, but our distance is now increasing. So plugging in all of our values, you should get an electric field of 2.5 Newton coulombs. Again, we can see from this relationship that our electric field is going to start decreasing dramatically as our distance increases just by a little bit. And for our last one, we're asked to solve for the electric field at point F. Again, plugging in all of our numbers, we get 1.6 Newton per Coulomb as our electric field. So as we plot that value, again, you see that dramatic decrease of our electric field as our distance increases. So we can plot all of this. Let me change color here. Connecting all of our dots. It jumps up when we reach our point C, and then again, as we move away from point C, it starts to decrease. Now again, all of that was for conductors. When we have insulators, things start to act a little differently. In insulators, again, we say that charges cannot move. So where they are placed during charging is where they stay. Now, A problem is going to tell you how the charges are being distributed. For example, you have a spherical cylinder has a uniform charge distribution throughout its volume. So we're going to repeat the previous example, but now instead of a charged sphere that's a conductor, it's going to be an insulator with its charge distributed throughout its entire volume. We're going to see that the only region that is different is the region between the center and the surface. So we're actually going to have charge at those points. Again, for the first part, if we're asked to determine the electric field at point A, we still cannot create a Gaussian surface around a point. So our electric field will still be 0 at the center. Again, this blue line is representing my Gaussian surface, so you're going to use it to solve for the electric field at point B. Now, again, the difference between an insulator and a conductor is now we're actually going to have charge distributed through the inside of this sphere. Now, remember that the density enclosed by the Gaussian surface equals the density of the actual sphere. So, by finding the total charge enclosed requires comparing the charge density of the volume enclosed by the Gaussian sphere to the volume of the actual sphere. So again, that density will be the same no matter what. Again, since we're going to be talking about volume, we're going to be using our rho. So the density enclosed by the sphere is going to be equal to the density of the actual sphere. Our charge enclosed is going to be distributed over the volume of the enclosing surface, in this case our Gaussian surface, is still going to be equal to the charge of the entire sphere over the volume of the entire sphere. Again, that ratio is going to stay the same. So our charge enclosed is going to depend on how much we're enclosing, and then the volume enclosed is going to depend on the volume of our Gaussian surface. Charge of the sphere will be the same, and our surface of the sphere will also not change. Now, to clear up some confusion here, our Gaussian surface is always going to be represented by a lowercase r, and our actual surface will always be represented by a capital R. Think of our equations always include a little r, so that's something that can change, like our Gaussian surface radius can change. And our capital R is going to represent something that cannot change, in this case, the actual surface of this insulating sphere. So we can clean this up a bit. Okay, so we can say that our charge enclosed is going to be equal to the charge of the sphere. Our pi's will cancel out, our 3's will cancel out, and the 4's will cancel out. So we're left with the radius of our Gaussian surface cubed divided by the radius of the actual sphere cubed. And this is going to be our charge enclosed. So again, using what we just derived for our charge enclosed, we can still use the equation that we've been using up until now, which is our electric field is equal to K, Q enclosed over R squared, and replace our charge enclosed with what we have now. So we have K, R cubed, QS, R cubed, over R squared. Again, this R was the radius of our Gaussian surface, which is still located at point B. I'm just going to draw it with my pencil here. We can simplify this to get our electric field is equal to K R Q S, which is the charge of the sphere, over R cubed. Now that this equation represents our situation here, we can plug in all of our values. Little r, remember, is the radius of our surface, our Gaussian surface, so in this case is 1 meter. Qs is the charge of the sphere. And then capital R is the actual radius of this this sphere. In this case, it'll be from here to here, which is 2 meters. And make sure that you keep it. Here you're going to get a value for the electric field of 5 Newton per Coulomb. Okay. Again, we saw that we had 0 at the point center. Now at point B, we're going to have 5 Newton per Coulomb. Now this part says, again, to determine the electric field at point C. Well, at point C, we have the exact same situation that we had with a conductor. Now our total charge is being enclosed, so we can use the exact same equation or the same situation that we solved for when we were solving for a conductor. With all of our values, remember that we got 10 Newton per Coulomb. And because now it's not changing depending on our increase in radius, the situation that we solved for in the conductor is going to be exactly the same for this situation. All that changed was when we were solving for electric field inside of the insulator. So for at point D, we had a 4.44 Newton Coulomb. At point E, we had a 2.5. And at F, we had a 1.6. So connecting the dots. We have a linear relationship inside of our insulator, and then an inverse square relationship outside of our cylinder, our sphere. Another way to solve for the electric field at point B is to find the electric field of the actual sphere, again using our equation, and the field strength increases in a linear manner from the center to the surface. So we can multiply the equation above by R over R. Again, this is just a ratio. So if we multiply our electric field by a ratio, then we can derive the equation that we use to solve for the electric field at point B. In the previous example, all of our charges were positive, so you saw what our graphs would look like. Now, if the charges had been negative, you would just use the upside down or inverse version, and this would be below the axis. In this last example, we're asked to solve for the electric field around a cylinder. Now, again, we're using a different shape here. If we view the cylinder from the end, it looks like a circle or a sphere, so that's how we're going to represent it. Again, the calculations will be different, but we're going to look at it this way. So be careful to read the problem to see if it is a sphere or a cylinder. Remember to also think in 3D. Again, we have to start from the very beginning because we cannot use the same equation. Since we use the other one for a sphere, which is 4 pi r squared, that's not going to be the situation here. So, starting from the beginning, if we draw our Gaussian surface correctly, our electric field will still be constant, so we can pull that out of the integral. And our change in area will now be the surface area of a cylinder, which is 2 pi r L. So to solve for the electric field, again, we saw from the beginning that in this case, we're going to think of a cylinder as a long, thin wire. So our linear charge distribution here is Q over L, the charge distributed over the entire length. So wherever we see Q over L, we can replace it with lambda. So lambda over 2 pi r epsilon naught is equal to our electric field. Now here we had R and L. R was going to be our radius for a Gaussian surface, and L is the length of this wire or cylinder. Now L is not going to change, so that was a constant in this situation. Again, in this problem, it says that a cylinder is an insulator with a uniform charge distributed through its volume. Now, that means we're going to have to compare our densities. So, the density enclosed by the Gaussian cylinder still equals the density of the actual cylinder. Density enclosed is equal to the density of the actual cylinder. So the charge enclosed per unit of volume enclosed is still charge of the cylinder over the volume of the cylinder. And our volume enclosed is going to depend on our R, the radius of our Gaussian surface, times the length of the entire wire. And the charge of the cylinder is just the charge on the actual whole thing over the volume of the cylinder, which will be pi. And we're going to use capital R to say that this is a number that does not change, times L. So our charge enclosed will be equal to the charge on the cylinder. Our pi's will cancel out. The L's will also cancel out. So all we're left with is a ratio of R squared over capital R squared. Again, remember that little r is going to represent the radius of our Gaussian surface, and capital R is going to represent the actual radius of our cylinder. So Q enclosed is what we're going to use to solve for our electric field. Now, we derived our equation earlier, which was Q enclosed over 2 pi r L epsilon naught. So now we can replace the charge enclosed with our new equation. Remember, little r is a radius of our Gaussian surface. We can have some things cancel out, and we're left with the charge of the cylinder times the radius of our Gaussian surface divided by 2 pi radius of the actual surface squared times the length of the cylinder times epsilon naught. Now let's say that our Gaussian surface is equal to the radius of our cylinder or greater. That means in the situation where our Gaussian surface is equal to our capital R, our little r is equal to our capital R, our electric field simplifies down to pi r squared L epsilon naught. One of the r's will cancel out, so that means that our electric field is going to start decreasing as R increases, by this relationship rather than 1 over R squared. And we'll see that in the graph. Again, these graphs, you're seeing it from one end of the cylinder. So if the cylinder is made of conducting material, it's going to follow the shape on the left-hand side. If it's made of an insulating material and the charge is uniformly distributed throughout its volume, it's going to represent the graph on the right-hand side. Again, the end part of it is going to be very similar, except the curve is a hyperbola instead.